Okay, so indeed, 5 days, it's almost over. And I just heard today that you guys were making a pizza party later this evening. And unfortunately, I cannot come because I have a flight to Delhi at 8:50. And although it's only 25 kilometers or so to the airport, it takes forever, right, to go there. And then, so I need to... Unfortunately, I was negotiating with Professor Sarkar if you leave at 6 or if I leave at 5:30. And yesterday we went only a quarter of the way and it took already half an hour. So I think I need to leave at 5:30. But anyhow, so I enjoyed very much being here with you and interacting with you. And if you should have any questions, doesn't matter if it's for the course material or if you would like to discuss maybe applications or so, send me an email. Write maybe in the header, in the subject line, write something like John Course Indoor or so, because I'm getting so many emails with applications and so on, and I always try to read all of them and I always try to answer all of them, but it really gets too many. And so if you write in the subject line of your email, if you want to contact me and want to make sure that it catches my attention, write something like John Course Indoor, and then I do this, right? And so please, if you have questions or if you would like to, I don't know, you want to apply somewhere and show and send me and say, is it a good cover letter or not or so, then just contact me and then we will have a look at this, right? And unfortunately, as I think stated also before, I would like to take many more students from India and postdocs. Funding is so tight in Germany these days. And I don't know if you look at the news these days, I mean, we are running from one bad news into the next, right? It's unbelievable that this happens. I'm almost a little bit sad for you that this happens. When I was your age, that was like 1989, 1990, I thought the world is becoming a better place. Germany was reuniting, Soviet Union was crumbling down. I thought we were doing a lot better. And now look at this 30 years later, with so many crises and so many conflicts. Okay, but anyhow, you guys are the next generation. You might make a change, and you might make a change with chemistry. And since it's probably unclear at this point if you should go to industry or academics, let's take just an example and discuss both. And this is the compound I would like to discuss with you, because there are probably 200 syntheses out there for this compound, both from academics as well as from industry. It's just one of the compounds which I'm standing in front of it. One of the compounds that really, really made a big impact, and although you can see it's not such a complicated compound. Do you actually know what we're looking at? Do you know that compound? So now new number here, careful, or new QR code. Okay, so one brave answer, two brave answers, three brave answers. So as you can see is that all these compounds I have put up here had some significance during Corona, but also even earlier when the first, and at that point we were afraid that it would end in a pandemic, but it didn't, around 2004, 2005, when the SARS epidemic hit, which did not turn into a pandemic, and so on. Okay, 77% for remdesivir, 23% for heparin, 0% for propofol, 0% for oseltamivir. The last one would have been the correct answer. So 0%. So that's good. So you haven't seen this compound. So that compound, oseltamivir, is Tamiflu. And let me just see. Okay, all the other compounds I have put up here, remdesivir was the one antiviral drug with relatively complicated structure, which during Corona was thought it's an antiviral compound. It might battle Corona, and it's still up today. Again, millions were used for this drug. It was not clear if it really helped. There were studies who said if you have Corona and you don't take remdesivir, it takes 2 weeks. And if you have Corona and take remdesivir, it takes 14 days. And so it was not really clear the benefits of this. Heparin as a blood thinner was also not really clear how much that worked. Propofol is an anesthetic. That is when you undergo surgery, you might get propofol in order to have that anesthetics. Michael Jackson overdosed on propofol because that also, when you take it as a recreational drug, makes you more happy, more relaxed, and so he apparently took too much of that, and so that's what he died on. And during Corona, indeed, propofol was very important because when you had this lung problem and needed to get intubated, that's of course not a very nice situation. You had to be put under anesthetics, and that's what they used propofol for. And we ran worldwide, we started to run out of propofol. Although propofol is a very, 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 very trivial, very, very trivial compound. And then again, it takes you. Let me just give this to you, just to show you sometimes how simple problems can be, and still how complicated it can be to have word supply. This is propofol. Cannot really be a lot easier, right? 2,6-diisopropyl phenol. And still we suddenly had during Corona, we had a worldwide shortage because we couldn't produce it long enough, but especially a shortage in Germany because many of the drugs actually are being produced for Germany in India. And suddenly everybody needed this, right? And so that was a very grave situation. So again, let's look at the compound again. This is oseltamivir. That's the rational name, or the name which was used in the literature. It's not the trade name. The trade name is Tamiflu. And so Tamiflu is a drug against influenza. But it was also thought that it's very good to battle SARS. And then one of the first drugs which were evaluated when Corona hit us, that they looked also at Tamiflu for Corona, but found immediately that it's not effective. But in 2004, when we had the SARS epidemic, then Tamiflu was supposed to be the one compound which everybody thought that this might be good. Our government in Germany, we bought for 50 million euros, we bought Tamiflu doses. So in order that our government said we need to be able to have a dose for every citizen in Germany, and we have about 80 million, and so you can see what we did. Unfortunately, we didn't need it, and so they stocked up on Tamiflu, and we didn't need it, and so you could say, oh, not a problem. So next pandemic might come, so we use it then, right? Not possible. Tamiflu expires after a year. You cannot store it for longer than a year. So essentially, we bought it, and we didn't need it. Fortunately, this is a good side, of course, but we could also not store it. It had to be destroyed. Okay, so this is Tamiflu, and at that time, 2004, 5, 6, many academic groups who did natural products broke up in a frenzy and said we need a synthesis, and then obviously industry needed that too. And in Europe, especially Hoffmann La Roche was the one company who really produced it. And as you say, we bought just Germany alone, we bought so many doses. We are talking ton scale here. And so simple compound, right? It's a cyclohexene derivative. If you analyze this, it has 2 amino groups. It has an alcohol group. The alcohol group has a funny ether connection, why so ever, but it has a funny alcohol. And then also it has an alpha-beta unsaturated ester. So if that would be your master or your PhD project, throw onto me a few general, I don't know why this is black here, it was supposed to show the structure of Tamiflu again. Throw onto me a few general approaches. You don't need to be very specific. Like, how would you consider, how could you think about to make this compound? Right? And I showed them to you on the previous slide here, right? You have a cyclohexene ring with lots of functionalities. What would you consider to build up in general such a compound? What type of strategies would you think might be good? I have it even two times. Funny, okay. I'm not sure what is happening here with the poll. I have it 2 times. The question is on different. No ideas. Cannot be. I don't know. Think about this. Shikimic acid. I'm not even sure what this is. Someone must be very good here. Shikimic acid. Very good. Let's see. Maybe I know what it is. We will see about this. So shikimic acid. So what you would do if you think about this, and shikimic acid is a good point, you would look if you have available from nature some compounds which might be already pointing into the right direction. So a so-called chiral pool approach, right? You take a compound which might have good availability, and then you say, okay, maybe I can modulate this, and then I can do this. So shikimic acid, indeed, and that was something Hoffmann-Roche did. Initially, at least, they had a synthesis starting from shikimic acid. But there was an interesting thing. I show you shikimic acid in a moment. Then they did the calculation and say, so how much do we need if we want to satisfy at least Germany for the doses? And they found out initially that the world supply of shikimic acid would not satisfy this. So, but in general, chiral pool is a very good idea. Quinic acid, yes. So somebody's sitting here who knows all the compounds which have a similar structure to Tamiflu. So indeed, quinic acid and shikimic acids are the 2 ones Hoffmann-La Roche immediately considered to use. Yeah, also oseltamivir phosphate, that's the product, of course. If you think about the structure, right? 6-membered ring, cyclohexene ring. What comes to your mind as a general strategy for a reaction? What type of approach could you consider to? How do we make 6-membered rings? One strategy which might come into mind is Diels-Alder, right? Diels-Alder, butadiene, some kind of a diene, and an alkene might make a 6-membered ring. Where else do we have 6-membered rings available, and where can we actually manipulate 6-membered rings very well? What type of compounds, what type of compound classes? Aromatic systems, right? Arenes. And we know very well how to put functional groups into arenes. We have all these tools, electrophilic substitution. We know how to put in nitro groups. Because look at this again. We have amino groups here on that 6-membered ring, right? So maybe putting in an aromatic system, putting a nitro group, reducing it to an amine. That's something we can do very well. Putting in alcohol groups, phenols, we know how to do this well. Putting on ester groups, right? Friedel-Crafts type chemistry. So arenes might be a good possibility, but here, of course, we have a cyclohexene type ring, And so, but we can hydrogenate an aromatic ring. So then this might be also a good approach to synthesis, to such compounds. And I will actually show this to you. I think that is something Hoffmann-La Roche developed in an also academic, spectacular way, how they used an aromatic starting material to make this compound out of this. So let's look at a few, and I know I need to be careful that I'm not again running over. So let's look at this idea of cycloaddition, exactly. And so now you are walking in the steps of Nobel Prize laureate E.G. Corey. Because E.G. Corey has one synthesis out there which makes use as the key step, makes use as of a Diels-Alder reaction, and here is this sequence which Corey is using, and this is, I think, it's a very, very nice synthesis. But we need to think about now, if you go to your boss in your company and you say, we should produce on ton scale now Tamiflu, and who could do this better than a Nobel Prize laureate, right? So let's do on ton scale the synthesis E.G. Corey and his group had published in order to make this compound. Let's consider how useful this is. So let's look at some of the reactions. So Corey is using butadiene and this acrylate. And you can see here already the first step what he's doing is he's using not a normal methyl ester you might have been used. He's using the trifluoroethyl ester. Why is he using this? Because that makes it even more electron deficient, and butadiene, and we talked about this, and in the 4+2 cycloaddition, you need to come this homo-lumo gap, you need to come as low as possible, and so he's taking an electron deficient, even more electron deficient ester with this trifluoroethyl group to bring that gap together, right? Because butadiene typically is not the most reactive. It's not the most reactive diene in the Diels-Alder reaction. And then very nicely, look what he's doing is he's catalyzing this with a boron-Lewis acid. And the boron-Lewis acid, of course, is coordinating to the ester group, and in this way brings that even further down. And Corey is using a very interesting type of Lewis acid. So we all know that boron, which has boron with 3 ligands, is Lewis acidic, right? That's because it still has the force coordination side open and can act as a Lewis acid. But look what he's taking as a ligand. He's using a ligand, it's essentially a proline type ligand, but look at the nitrogen. That nitrogen when it coordinates to the boron, is a positive nitrogen. So that is not a very strong ligand that in order to do this coordination. So essentially he's coordinating with a tri-substituted amine, and this way he builds up a positive charge here next to the Lewis acidic center. So that makes it even more reactive. And then he is the Lewis acid he's using is chiral, so it has a chiral center. And this way there's a chance to do this reaction enantioselectively. And that's what he's able to do. So he's able to do this Diels-Alder reaction, and you can see he gets 97% yield. That's pretty cool. He gets 97% EE. This is really nice as well. And so he's able to do this. And then very instructive, I just want to go over a few issues here. It's very instructive how he's introducing the nitrogen, the amino groups, and that is something which will concern us in the industry synthesis also a lot. So what he is doing is he's converting this ester into an amide, and then he's using a reaction you might better know if you have a carboxylic acid here, but he has an amide, he's using an iodolactamization. And this iodolactamization works in the way that you have iodine. We talked in the electrochemistry a lot that this is like an equivalent for iodine plus, iodine minus. And so if the iodine is coordinating to the double bond, let's get some of the pens here. So you are forming the iodine plus. Here it goes up, and you've seen I've drawn this with an iodine on top, but I could have also drawn this. The iodine could also have come from the bottom, the I plus. So we have the NH2 here. And the beauty of this reaction is that this is reversible. And iodine, the iodide minus you will still have there, will not attack this iodonium ion, because making a iodination on an alkene is thermodynamically not good, because it makes two weak carbon iodine bonds. And so the beauty of this is that once you have these iodonium ion, you need a better nucleophile, and the better nucleophile is your amino group here, and the amide. And you can see here then, this attacks the iodonium salt and forms this lactam. And the good thing is, because this stereocenter is down here, it can only do this, and only can reach this center if it also comes from the bottom. For the iodolactonization, it doesn't matter if the iodine comes from top or the bottom, because it's reversible. And only when it comes from the top, then the nucleophile will kick it in and kick it out. If it comes from the bottom, nothing can happen, because it's an SN2 reaction, and then it comes back. And so that's an interesting fact here, right? This is the first amino group Corey has installed, and in this case. And then he's doing a couple of more reactions. I do not want to go through this, but if you're interested, it's interesting to read the paper. It's a JAX communication which has only 2 pages. Half a page are references. So pretty cool. You could see how important that chemistry was considered. All he had to do is essentially say how to do it, and then he gives some explanations to these type of reactions. So then what he's doing is, let's just go quickly. He's protecting an amino group. He is eliminating. He's now eliminating this iodine to the double bond, because we need a double bond here in the end. Okay, it's not seen, the Tamiflu here. And then he's doing an allylic bromination, brings this back, and he's doing another elimination. So you see what he's essentially doing now, he's converting this iodocyclohexane by addition elimination chemistry. So first elimination gets the double bond, then allylic bromination, and then another elimination to get the diene in here. So he gets this intermediate. And you can see, and also he's cleaving the lactam, and now you see he has a stereocenter here. The stereocenter here originally here is lost, but he had transferred the chirality to this position. And then again, he's doing a bromoamination. I showed you our variant of an iodoamination. We are actually interested in see if we would make this compound, if our protocol for the iodoamination might also work here or not, right? And by this iodoamination, you see now it's interesting to see he's installing the second amino functionality he needs here by making an aziridine, and then he opens up the aziridine with this alcohol we need in the Tamiflu, and we have 2 possibilities to open up the aziridine. The nucleophile has to come from the bottom because it's an SN2 reaction, and you see if it would come on this carbon, then the neighboring substituent would be in the way, so this is sterically more hindered. If it comes onto this carbon from the bottom, it will install this, and then what he had to do is, and then again very cleverly, he has 2 different protecting groups, how he brings in the amino functionalities, and one is very acid labile. He can selectively deprotect the Boc group and then make the ammonium salt, ammonium phosphate, which you need. So very nice, and I think in his in his title he says something like a short synthesis of Tamiflu, and I think we can count the steps. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's 11 steps. So I would say it's a medium-sized synthesis. So now, as an employee of the company, you have read about this publication, and you go now to your boss and says, okay, I know, or Corey has shown us how to make Tamiflu. Now we make a ton out of this. How would you evaluate this synthesis? How would you, if you look at what was accomplished, do you think this is good for ton scale? I thought I had a question to this, but anyhow, maybe we leave it there. What do you think are weak points to do this chemistry on large scale? If you look at the sequence. Sorry?
More steps.
It's many steps, yeah, but we will see. You will see that it's a relatively complicated structure with stereo centers, groups, and so on. You will see that the industrial synthesis I'm going to show you, that also has steps. There's no difference in that. But are there any steps where you would think maybe that is not so suitable if I would like to do this really on scale, if you evaluate this? So you have a lot of steps where you fiddle around with the functional groups. But I would like to draw your attention right away on the first Diels-Alder reaction he's doing. What do you think if you evaluate parameters for that as a catalytic Diels-Alder? How would you evaluate the conditions that catalyst is operating? Look at this, what we're needing. You need 10 mole percent. That's already a pretty high catalyst. We can probably calculate the molecular weight. You see, 10 mole percent means one equivalent will be converted by 0.1 equivalent here. So the mole percent is the one parameter you want to look at, but the weight percentage is another one, right? And look at this. You have a product here which has 6 carbon, 7, and let's count the oxygen as a carbon as well. So 6, 7, 8, 9, 10, 11, and then 3 fluorine atoms. Let's say we have about 14 atoms and more or less molecular weight of on average on 15. So we're making a compound which has like a molecular weight, let's say, of 320 or so. Look at our boron catalyst here. So this has, again, it has 5 atoms here. Then it has 2 phenyl rings, so 12 more coming. So that's 17, 18, 19. Then the boron 20. We have a toluene group that has another 6 atoms here. 7 because it's a toluene. So 23. So that catalyst has a higher molecular weight than your product. So if you not consider mole percentage, if you consider weight percentage, you're probably around more than 100% of weight percentage. So in other words, for 1 kilogram of product you might make here, you will have 1 kilogram of catalyst. It might be recyclable, but it might also be waste. And so that is one point which is of course difficult here. Look at the reaction time, 30 hours. This catalyst, it's attractive, it's room temperature, but this catalyst, it makes 10 turnovers in 30 hours. This is 1 turnover every 3 hours. Think about this. That's a pretty lazy coworker, right? You would not, amazing. So this step alone is, I guess, very difficult to scale up and make that useful, right? I think all the other steps are okay. What is nice, of course, is that you are installing the stereochemistry. You start from very inexpensive starting materials. These are clearly pluses, but the catalysis which is involved here is not really good. So let's look at this, and again, let's look at the approach of Hoffmann-La Roche now. And I very much, it's public domain, it's open access. I very much, if you are interested in reading more about the story, this is a fantastic article by Karpf et al. These are the Hoffmann-La Roche people, and they do not just list synthesis by synthesis, they also tell the stories around this. And I think this is always very valuable just to hear a little bit about this. And it's fascinating to read. And so in this making these antiviral compounds, they considered oseltamivir, but there were also other compounds available, but it was clear that this is probably the best. And so that's what they assessed. And so then there was first the discovery process. And in the discovery process, they said, it's enough if we have a few grams. Let's get that compound as fast as possible so that we can evaluate this. And here you see, here's one of the compounds which people have mentioned, the quinic acid. And here's the Tamiflu again. And if you look at the structure of quinic acid, I think you will immediately agree that this is maybe a very good starting material for this, because you need to somehow eliminate that hydroxyl group. And then you have the three other functionalities. You somehow selectively have to exchange two of the hydroxyl groups for the amino groups here. So that looks doable, right? And nevertheless, look at the steps. In the end, somebody just said steps. So that's 6 steps. They made this epoxide. So essentially, they did the elimination, and then they had to differentiate somehow the hydroxyl groups that they could make the epoxide only here. Then it took them 4 more steps by ring opening, ring closure reactions to convert the epoxide to an amine. Took them 4 more steps to introduce a second amino functionality, because we need in the end a diamine. And then they were open again, like Corey did. They were able to open the aziridine on this position, get the alcohol in there, and then get it on there. So that's again, it's 6, 10, 14. I'm not sure if this was done in one pot or not, but let's say it's not. 15, 16, 17, 18 steps. Ooh, that is, so Corey is right? And he publishes and says short synthesis. So his stepwise, his synthesis is definitely shorter. But the nice thing is here, you bring in the chiral information from the chiral pool. This was good. And so it allowed them at that stage to evaluate the chemistry. And one thing they were interested in is this alcohol, this 3-pentanol, is relatively expensive. And so the interesting question was, could you exchange that alcohol for something simpler? Easiest case, could we make a methyl ether here, right? Using methanol, ethanol, propanol. You see what they tried. And the interesting thing is, indeed, the biological activity is very dependent on that alcohol group. The smaller the number, the better, right? These are the IC50 values in nanomolar. This has an IC50 value with this alcohol of 1 nanomolar. If you go to methanol, you go 3 orders of magnitude, you go down. So they very quickly decided that this is indeed the target they should pursue. Okay, so this was quinic acid. And then they had a few more issues, and let me tell you about this. So the quinic acid came from a bark of a tree, and they said, they calculated and said, how much do we need? If we develop a chemistry based on quinic acid, how big can our scale up? If we close our eyes and we can do it as big as possible from the chemistry we want to develop, will we have enough quinic acid in the world in order to do this? And they did the calculation and they decided, no, we don't. There's not enough quinic acid on the world to satisfy the demand we have. And then let's look at, again, what people think about sometime in industry. So nevertheless, they had this synthesis I just showed you before. They made they made a few steps, but they had also a few low-yielding steps, right? So that is something which was not so good. And then they did also some protection chemistry where they would, for example, exchange this acetal, which they had made in the beginning of the synthesis. This is an acetal of acetone, where they would exchange it for the pentanol. That was the ether, this funny ether group you need in the end, right? It's here still as an acetal. And in order to do this, they used as an acid catalyst, they used perchloric acid. That's not a good idea either. And so perchloric acid is explosive. And so you don't really want to use this. And again, a word of caution is, we had, especially at universities, we had terrible accidents with perchloric acid. And I tell you how that happened. Especially our friends from inorganic chemistry like to use perchloric acid a lot. And so all is fine, small amounts and so on. They didn't really do it a lot, but the point is, it's kind of volatile. And so what happens is the perchloric acid gets absorbed very, very well by wood furniture. For example, by the wooden hoods, right? I'm not sure, I haven't seen your labs, I think. Your hoods, they have plastic polymer also, or they still have wood outside? They have plastic already, right? There's a good reason for this, because the wood is absorbing very often lots of chemicals. It's porous and so on. And so the perchloric acid, if you would have a wood hood, would go into the hood and into this wood of the hood. And over time, it would accumulate more and more and more. And then finally, the university came and said, hey, we renovate your labs. We give you money for new hoods, and we do this with, we use the plastic, the polymer-like coatings. So in order to dismantle the old hoods, then some workers came in, and then with axes and so on, they dismantled the hoods, they destroyed it. So they went there and they cut, or with a saw also, they cut the hoods. And then that was the moment it exploded, because these wooden frames had absorbed so much perchloric acid that then when you would go there with force, so that's sensible against pressure and also against fire, when you went there with an electric saw, it would just blow up, and really in a terrible way. So that is, again, so the safety concern here to use this acid, again, this is what the people did in the lab on a small scale. You go to your process people and they say, no, we don't want this, right? And then there are some other issues. The introduction of the amino groups is being done with azide. And that is a terrific nucleophile. If you use azide as a nucleophile, you open up, for example, this aziridine here. These reactions were really fantastic. But again, the point is that azide is dangerous. I had some more issues here. They were reducing this azide to an amine, and they did a Staudinger reduction. You can do this with palladium on charcoal. You can make an azide to an amine. They were kind of afraid that they might hit the double bond here. So a very reliable way to reduce an azide to an amine is that you use a phosphine. You do a Staudinger reduction. Trimethylphosphine stinks terribly. And so again, that is a great reaction, but in a production setting or so, where you might not be able to control always the emissions, it's not a good reaction. So again, the chemistry work, the lab people were proud on themselves, and the process people said, no way. There's so many red flags in your synthesis. And so that was essentially the first generation, the summary. So here you see the quinic acid. The shikimic acid already has the double bond installed, and this is the double bond you need here, right? So the shikimic acid and the quinic acid are differing by the elimination here of that hydroxyl group. And the quinic acid, anyhow, because it comes from the bark of a tree, was not so attractive starting material. But for the shikimic acid, in the beginning, you couldn't find good sources, but very quickly it was found that it is in plants in China. You can grow this and extract it from that plant. But also, because obviously in Europe we didn't want to be so much dependent on the source from China, Hoffmann La Roche also found out very quickly, and they are very great in fermentation technology. They found a way to make shikimic acid on ton scale to do this, to have it as a starting material. And so with this, they had quite a number of good syntheses, but there were issues, and one of the big issues is to avoid azide in industry. And so rather than opening up the epoxide with azide, they wanted to open up the epoxide with the amines. But let me ask you this, what is in general, so you have a leaving group, what is in general the problem if you want to open up, I don't know, let's say an epoxide, what is in general the problem in this nucleophilic substitution of amines with epoxides or halides or so? Why is that something which is not straightforward in difference to the azide? And if you think back maybe in your basic organic chemistry, you have not done this for an amine synthesis. You did something like a Gabriel synthesis. That is, right? So if you think back about Gabriel synthesis, you are not using ammonia or an amine. You were using the potassium phthaleamide. And then maybe you do the nucleophilic substitution, you generate the phthaleamide, and then you hydrolyze this, and you're getting your amine and phthalic acid. So why can you not do it directly? What's the problem if you use directly an amine? Why do you have to go through a phthalic acid, ester, or the reagent? I'm not sure if I have this. Do I have this as a question? No. Any idea what is the problem? It's first year organic chemistry. I know, it's the 5th day here, so you guys are hanging in the ropes. I fully understand this. Why can you not synthesize amines by nucleophilic substitution with an organic halide? And the reason for this is that when you generate your amine, you see here in this case, the example I've chosen, this is a primary amine. Now I do the opening, it has an alkyl group here. This is a secondary amine. Which one is the better nucleophile? The primary amine or the secondary amine? It's a secondary amine, right? Because it becomes more electron rich. The alkyl groups are donors. And so the problem is that this secondary amine will now react preferentially with your electrophile, for example with the epoxide. And then you are forming this tertiary amine. Now we have a tertiary amine. Which one is the better nucleophile? The tertiary amine, the secondary amine, or the primary amine? It's the tertiary amine. So you go from a less reactive component to a more and more reactive component. And that is in general the problem in the amine synthesis. And this is why we need to use phthaleamide here. That's the Gabriel synthesis. You see this one here, this has here of course 2 electron pairs. This is nucleophilic. But once I do the first substitution, this is not nucleophilic any longer because that lone pair is now distracted in the resonance here. And the same thing with azide. Azide can only do one nucleophilic substitution. This is why azide is so great, because it's a great nucleophile, but it cannot give you this over-alkylation. And so then, nevertheless, what they tried here at Hoffmann-la Roche is, and they came up and they tried conditions, adjusting the amount of benzylamine. They used very good Lewis acid, ytterbium triflate. Ytterbium is very oxophilic, so this activates epoxides very nicely, and they were looking at this, and so they could, in a way, they could get the monoamination going, but they activated the epoxide with the ytterbium so much that it would open up in an SN1 type reaction, and you would have a Rieger selectivity problem. So you see they got this, and then actually once under the Lewis acid interaction, they would start seeing elimination of the alcohol, and they would eliminate so many of the groups here, both the water and also the amino group, because it would go into an aromatic system, and that was a severe side reaction that they could not do it. So again, this was a problem, and then in the end, don't really ask me why, but they found conditions. They found that allylamine was really good to not give them these over-alkylation chemistry. They found very specific conditions to do this substitution, and then continue on in the synthesis with having where they introduce the amino groups, and they do this again. They do this in the second type. The second amino group ultimately is introduced by nucleophilic substitution of the allylamine, and they had conditions which allowed them to overcome this problem of over-alkylation. And so this way they had a good synthesis, and you see here now, it's the overall yield is spectacular. The number of steps is still pretty high, but the yields they have overall, the worst sequence they have here, one step is 70%, one step is 77%. Many of this is quantitative, so that is pretty good. Okay, there's some more things. Now I would like to show you a shikimic free route, and as I say, this is, in my opinion, a synthesis which is not only from industrial relevance, because they could do it on a really good scale, but it's also from an academic point of view, it's a fantastic synthesis, in my opinion. And so what they did here is, you see they start from a aromatic precursor. They start from a phenol which has these 2 methoxy groups outside. This was commercially available, and so you could buy that, and for relatively little money. They installed, in the first step, they install the alcohol group. They need here simple William ether synthesis. You deprotonate the phenol, and then you do a nucleophilic substitution on the mesylate. And then also very nicely, they do a very selective and high-yielding dibromination. I could ask you, why are the 2 bromines, so you do double bromination, why do they go in these 2 positions? Why are they not going into this position? Can you see this? What is the reason that selectively this goes into these 2 positions? I need to, okay. Any idea? How do we analyze this when we go and say auto-power meta selectivity in electrophilic substitutions? A phenol is a donor or an acceptor in the OH group? It's a donor, and that is auto-power, right? Very good. So then we have already probably everything. So this methoxy group here, this methoxy group and this methoxy group wants to do ortho-para direction, these two. This methoxy group wants to do ortho-para direction. And only this hydroxyl group wants to do the direction here. So two groups say, hey, bromine, this is where we want you. And only this group says, you should go here. And so because the plus M effect of these two groups goes to these two positions, this is indeed what you're observing as the product. And then also very nicely, what they do is a type of palladium catalyzed installment of an ester group here. And this is again a really, really, really good reaction. This is, you have the aryl bromide here. And let me show this. This is like one of these palladium coupling reactions, but it's a palladium coupling reaction which is a carbonylation. And so in this case, you make the oxidative addition with a palladium zero catalyst, as you always have, and then once you have this, if you have carbon monoxide as a pressure there, carbon monoxide pressure, what you do is this coordinates first to the palladium, and then it does an insertion. And then in the presence of methanol, or ethanol, because they're making the ethyl esters, you exchange the halide group you had here, so your X is originally the bromide. You exchange this for the alcohol, and then if it's doing a reductive elimination, it is installing the ester group. And look at this. This is a pretty good, so first of all, I think I don't know if you know it or not, all these type of palladium couplings is palladium zero, right? But you see here that what they start here is a palladium 2 plus salt. But that is, in all these palladium coupling reactions, is very easily possible, because if you use a phosphine ligand, and you typically use a little bit of an excess, palladium 2 gets reduced by phosphine ligands very rapidly. There was a publication who showed this. If you use palladium acetate and triphenylphosphine, and you need traces of water, you make essentially palladium 0, 2 molecules of acetic acid, this is where your acetate goes, and you make triphenylphosphine oxide. This is, by the way, something you need to be aware of if you do asymmetric palladium catalysis, that if you start from a palladium 2 precursor and you have a chiral phosphine ligand, you destroy, in order to make the palladium 0, you destroy part of your ligand. So you need to adjust for this if you want to do this approach. And look at this. This is pretty spectacular in my opinion, what they have been able to accomplish here. They have installed these two ester groups, 95% yield. That's pretty cool. They do this with 0.5 mole percent of palladium. This means, because they do it twice, right? That's 0.25 mole percent for each of the ester groups. So 0.5 mole percent. But doing this twice, that would be a turnover number per ester group of 400, right? I think, I'm not sure if I calculated this right here, but I think so, right? So that's a very, very good reaction. The other thing to realize here is the reaction times are still relatively long. High temperature, palladium chemistry is really robust against high temperature, so they could do this. And this DPPP is their phosphine ligand, which they were using. So they're making this, and now they do a hydrogenation of this arene molecule. And the interesting thing is, if you do a palladium, or they do ruthenium on aluminum oxide. So essentially you have you have a support, you have your support and your ruthenium catalyst, and the same is true for palladium. And then if your arene is approaching this, and your catalyst is activating hydrogen, the hydrogen is simultaneously delivered all from the same side. So if you hydrogenate an arene, it's always a cis addition on the whole arene ring, because you can think about this, it comes like an UFO, right? It comes down, and then the hydrogen, it picks up the hydrogen from the same side. So then they are able to make this compound here in this hydrogenation reaction. Now here's my question. Now we have here 5 stereocenters. Is this a chiral compound? Why is it not a chiral compound? Has a plane of symmetry, right? Has a plane of symmetry. So if we look at this, this is still achiral. And so they still are not dealing with any types of stereocenters at that point. And for some reason, in the next point, they take off the methyl groups here with a good nucleophile. Let's not go into this. And then here comes the decisive step. They're doing a desymmetrization. So what they do is with an enzyme, the enzyme will only saponify one of the 2 ester groups. Now, is this molecule now chiral? Yes, it is, right? Because I have broken the plane of symmetry by going from the ester to the carboxylic group. So now they suddenly have an enantiomerically pure compound, and they have found an enzyme which is doing this, and it's the most cheapest pig liver esterase you can buy from Aldrich, and it costs nothing, right? They found, and it is hydrolyzing esters very well, and they found that it is very selective in doing this. Let me just when do we start? When are we supposed to stop? What does the time schedule say? Because I don't know, I don't want that all you remember from this course is that he always did too long. So this says 12:45, that will be in 3 minutes. 5 minutes. Let's quickly think about that strategy. A desymmetrization compared to a kinetic resolution. What is the difference? So if I have a desymmetrization, and this is what they are having here, then you can have a symmetrical compound. Let me use this diol. This is achiral. And now you need a chiral reagent. A chiral, like in their case, it's an enzyme or so. You need a chiral catalyst. And let's say you need, and you use a acylation reagent. So let's say we're using acetic anhydride. And now what it needs to do is, it needs selectively to react with one of these 2 enantiotopic alcohol groups, right? These 2 groups are enantiotopic because if you selectively functionalize the one or the other one, you will produce enantiomers. So enantiotopic, right? These 2 groups here. This pen is terrible. Next time I want I write so nicely. Here I have my old lecture notes with me. I write so nicely with my iPad. This is much harder here. Okay, so right, and so the idea is that my catalyst will differentiate between the two enantiotopic alcohol groups, and it will make this compound. And so this is now chiral, of course. And the maximum yield I can have in principle is 100%. And this strategy differs from the strategy of doing a kinetic resolution. In a kinetic resolution, what you usually do is you're not taking a achiral so-called meso compound. In a kinetic resolution, you start with a mixture of enantiomers. And now again, the same idea, you have a chiral catalyst, you have a reagent. And now you make use that your chiral catalyst will react with one of the enantiomers faster than with the other one, right? The interaction of the chiral catalyst with your chiral substrate is a diastereomeric interaction, and so chiral catalysts with enantiomer R and chiral catalysts with enantiomer S are diastereomers, so the rates might be different, and therefore you might end up with the one enantiomer which is untouched, and the other one which is functionalized. So this is the so-called kinetic resolution, and here, of course, the maximum yield can only be 50%. Right? So the desymmetrization typically is a nicer approach. And then finally, there's something like a dynamic kinetic resolution. If you have conditions which might equilibrate your two enantiomers, and I give you again a very well-known example which comes from Nobel Prize winner Noyori. He looked at the reduction of malonates. I'm afraid I'm too low on this. So you see, let me. So the dynamic kinetic resolution this is the example from Noyori's lab. He could take a racemate of these beta-keto esters. You see, this has a stereocenter, but you could use it racemically. Let me nevertheless give you one stereocenter, and let me draw both enantiomers here. And what he could do is, with his famous ruthenium binap catalyst, so this is in this case here the chiral catalyst. And with hydrogenation, he could hydrogenate the keto group. And he could do this selectively, so the delivery of the hydrogen would be enantioselective on that keto group, but the catalyst would only react with one of the two of these enantiomers. But then if you do this under basic conditions, you can equilibrate these two, because this is a proton which has a pKa of about 10. And so under very mild basic conditions, you deprotonate, reprotonate. So you equilibrate this, and then your chiral catalyst will only react with one of the two enantiomers. It's doing selectively the reduction. And so this way, from a racemic molecule, you come to the enantiomerically pure molecule. And in this case, again, the maximum yield can be 100%, because we're equilibrating now the two enantiomers. This is a very strong, very strong technology, and which they are able to do. And so in this case here, the Hoffmann-La Roche case, they made use of a desymmetrization, where they had the symmetrized compound here, and then selectively were able to hydrolyze one of these reactions. And look at this, yields and enantioselectivities, really fantastic. And so we're not going to do anything a lot more now. In order to, once they had this, they have been able, you see now they are putting in the carboxylic acid, converting the carboxylic ester into the amino groups, and they do Curtius type rearrangements. I'm not going to go into this reaction. If you don't know, don't worry, but you can rearrange a carboxylic acid into an amine with this type of reagent, DPPA. Again, the difference, the problem with the DPPA is it's an azide reagent. It's this reagent, and it takes a carboxylic acid, the acyl azide, and this in the Curtius rearrangement will convert to the amine and carbon dioxide. Lovely reagent, lovely reaction, but again with the problem, it's azide chemistry, right? But still, that's how they got it on, and then they had to do a few more steps in order to produce it this way. And so, at least for Germany, they have been able to very rapidly satisfy the amount. So our government says we give 50 million euros, but we want one dose. I'm not sure how many doses actually they got for each. I think that it was on the range of 1 dose per person. So it must be 80 million doses or so. Pretty expensive. Of course, Hoffmann-La Roche wanted to also to showcase that they can do it. The strengths of Hoffmann-La Roche is indeed they have a biotechnology. They are very strong in biotechnology. So all these enzyme type chemistry, they are very, 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 very good at this. It's a terrific. I'm not sure. Is Hoffmann-La Roche also in India? You have branches here. I don't know. It's a fantastic. It's a great Swiss company which has also one site in Bavaria, relatively close to where Regensburg is. Okay, so only 10 minutes too long, right? But we started a little bit faster. So overall, I hope you like this. I enjoyed teaching here the last week very much, and so thank you all for coming here. The one thing I hoped I could do with this course is I didn't throw too many reactions at you. I think if you want to learn about reactions, you can take a textbook and just read about this. I was hoping more to get across ideas, right? What are people, how do you consider what is a good process, what is a bad process under safety issue concerns, under renewable resources. We talked about photo and electrocatalysis, which is hailed to be a new type of green methodology, right? And so we didn't do too many examples, I think, but hopefully you like to think about the ideas why this might be good technology and maybe not. And so I'm sorry that I missed the pizza party. I had already twice at this Domino's place where you will have it tonight. I already had twice a pizza, and unfortunately, I'm going to miss it. And they have the pizzas are very good. I can tell you, it's very, very good. So anyhow, again, if you want to get in contact with me and discuss some things on future perspectives, send me an email. Do the subject like Jam course indoor, otherwise I might overlook it. And then maybe I have the chance to see one or others of you too. Again, at least from the students from indoor, I will come regularly. It's already my third time. I will probably come back this fall again. It's always lovely to be here. And so I enjoyed myself very much. So thank you very much for coming here.